to the AIMCOM workshop, and we are come to the session C. In this session, we have two speakers. The first speaker is Aditya Dhakal from University of California, Riverside, United States. The title of the talk is Machine Learning at the Edge, Efficient Utilization of Limited CPU-GPU Resources by Multiplexing. Let's welcome. Okay. Aditya, I guess you are here. Yeah.
Okay, hello. Can you see my screen now? Hello?
Yeah,
Yes,
currently,
yes,
yeah.
Okay, let me start then. Good afternoon, everyone. I'm going to present our paper, Machine Learning at the Edge, Efficient Utilization of Limited CPU-GPU Resources by Multiplexing. This work is done by me, Aditya Dhakal, my colleague Samir Kulkarni, and my advisor, Professor K.K. Ramakrishnan in University of California, Riverside. Use of machine learning applications such as augmented reality, virtual reality, speech translation, image recognition, autonomous driving are rising. These applications often are compute heavy and also require low latency. The user devices, usually smartphones, are incapable of providing enough compute for that low latency. However, offloading the computation to a distance cloud can have a high network latency and can therefore be unsuitable. Edge Cloud can offer those applications the required compute resource and provide low latency by being located closer to the user. These applications that I mentioned often use compute-intensive deep neural networks. DNN are compute-heavy, and they require specialized accelerators such as GPU for low latency inference. GPUs are a good hardware for DNN because GPU offer parallelism that can be very useful for accelerating the matrix convolution operation used in many DNN. To see a benefit of using a GPU, we conducted a small experiment with 3 different DNN models, DenseNet, ResNet 50, and VGG16. All of them are image recognition model. And we ran them in GPU and CPU. And please note that the y-axis of the plot is log scale. And we can see that use of GPU can lower the latency by a lot. Use of GPU can lower the inference latency by orders of magnitude. Therefore, a GPU is necessary to use this DNN and infer by using this DNN. Now, unlike the cloud environment where there is hugely scalable hardware resources, Edge Cloud can have some good hardware, but they are relatively modest in scale. So these edge-based ML frameworks need to multiplex the system resources such as CPU, GPU, memory, storage, network bandwidth, etc., so that it can serve a lot of requests for a lot of applications that it is hosting. So we have outlined a few requirements for an edge ML framework. The first being it has to judiciously share the GPU. The GPU is important for all DNN, but naive sharing of GPU shares GPU temporarily. Therefore, the GPU utilization is lowered. We have a method of sharing a GPU called spatial sharing, where all of the application can access the GPU at the same time. This spatial sharing is preferred because it will increase the utilization of GPU. The second point is since we are hosting a lot of applications, we will be receiving a lot of data in the edge, a lot of streaming data that has to be inferred. This edge server will have to move that streaming data from network to GPU with as little time penalty as possible. Third being there are many ML platforms like PyTorch, TensorFlow, TensorRT, MXNet. What people do with they design a DNN model and they train it using those ML platforms, and then they also deploy using the ML platform itself. So our ML framework will also have to be able to run these diverse ML platforms that exist today. And beyond the GPU, our framework should also be able to judiciously use CPU and other system resources. So we designed an ML inference and learning framework with multiplexing of GPU in the mind. We present the architecture of the ML this framework in the figure. Our framework is based on OpenNetVM, a DPDK-based network function virtualization platform. As we can see in the red rectangle, the streaming data that is coming from the NIC and the network is being processed by OpenNetVM and kept it in the OpenNetVM shared memory. So we further modified the OpenNetVM platform so that we can run these ML models as applications. These ML models will have access to this data from the incoming data from the packets, as well as will have access to the GPU in the system. And in our framework, we virtualize the GPU. The GPU is virtualized with help of an application called Cuda multiprocess service. Multiple ML applications then can run concurrently by spatially sharing the GPU resources. As you can see in the figure, we have given application 1 70% GPU, while application 2 30% GPU. I will explain in later slides how it is possible to give a required amount of GPU resources to each of the application, so that we can provide the isolation for each of the running application. And our SML application itself is divided into 3 different modules. The first being NetML, that transfers the data from the network stream to the GPU. The second being related to a DNN platform for loading the desired DNN model into GPU. And the third one being a module that receives the data from network, then executes the data inference in the GPU and gets the result back, a streams and GPU notification module. We have we use the testbed. We had a Dell server with around 20 cores of CPU. We have 256 gigabyte of memory. More importantly, we have a NVIDIA V100 GPU. It has 16 gigabyte of GPU memory and 80 streaming multiprocessor. This streaming multiprocessor, or SMs, are the hardware in GPU that are similar to CPU cores. We have experimented with the image recognition task. We have used a color image of 224 into 224 resolution. We chose this resolution because it is the resolution of choice by many researchers for training image recognition model, and you can easily get a pre-trained model suitable for this resolution everywhere. The image size comes out to be 588 kilobyte for each image. We have used a 40 gigabyte connection between the traffic generator that sends the image and the receiving server that is the one with the GPU that performs the inference. We send the image over UDP packets, and our experiments ignore the network latency for now, so we are only reporting the GPU, the execution time for doing the inference. Let's talk about now I will discuss about the streams and GPU module for running this DNN module and how we are spatially sharing the GPU. So I also said before, if you run 2 or 3 applications in default in GPU, the GPU runtime environment, such as CUDA for NVIDIA or OpenCL and open source one, will time share the GPU among different processes. This temporal sharing of GPU will interleave the GPU kernel. The kernel is a function that runs in the GPU. And it gives each of the concurrently running application equal time quantum for in the GPU. So everybody gets around 100 microsecond at a time. And all the streaming multiprocessor, or SMs, will be available for only one process. So there is no sharing. The entire GPU is given to a process or to a ML application for whole time quantum. So what results is ML application with lower compute requirement also get the same amount of time as an ML application with higher compute requirement. So the GPU can be wasted. Now, the better method to share GPU would be spatial sharing of GPU. The Cuda multiprocess system, an application, provides concurrent multiplexing of DNN model. This is called spatial sharing of GPU. The spatial sharing allows the kernel from different applications to run concurrently. And in that case, the streaming multiprocessor in the GPU will be, some of them will be available for one application, some of them will be available for other applications, so they will be shared. The spatial sharing, the Cuda MPS, has two different modes to share the GPU. One is a default mode. Here, the multiple applications run concurrently, share the GPU, but users have no ability to influence how much resource one of the application can get. The GPU subsystem determines how the concurrent applications share the resources. Then the other mode will be a controlled MPS mode, a controlled mode. Here, the users have ability to set a GPU resource for each of the application. This is done by specifying a GPU percentage before launching the application. So I will show an example of how the GPU is divided when we are doing a control mode sharing. To enable control mode, user has to determine how much GPU do you want to give. So the user will write, let's say 50% GPU for an application A. Then when the application comes up, it will have access to, in case of V100 GPU, 40 SMs. A V100 GPU has 80 SMs in total. Since we are giving 50%, the application will get 40. And similarly in figure, I have shown like how the GPU can be divided between three different applications. Let's say DenseNet gets 15% GPU, then it will only have access to 12 SMs. ResNet 50 will get 35, so it has access to 28 SMs. And VGG16 is getting 50% GPU, therefore it has access to half of the GPU, or 40 SMs. We have noticed that some of the DNN applications have limit on how many SMs they can effectively use. That is, after a point, if you give them more SMs, they do not improve the latency at all. And this, the latency will show diminishing return. But the point where the latency will show diminishing return varies on different model and also varies on the batch size we are inferring. Now, we will show the result of sharing GPU temporally and how it affects the latency of the running application. We measure the latency of three different DNN running together. We first brought up the DenseNet DNN, the red line, and we can see like when it comes up and running alone in the GPU, it only has a latency of 20 milliseconds. But as soon as the ResNet 50 comes up in 1 second mark, we can see that DenseNet, the red line latency has increased to 40 milliseconds. And when another DNN, that is VGG16, comes up at 3 second mark, we can see further rise of the inference latency. We can see the latency goes down when one of the applications keep turning off. First the VGG16 goes off, then the DenseNet latency also goes down, and so on. So we can say that the temporal sharing latency will increase with addition of each DNN application. Now we will see what happens when you have default or uncontrolled MPS spatial sharing. Here, again, the DenseNet comes up at first without any other applications running. It gets a latency of 20 milliseconds. Now, when the ResNet comes up at 1 second mark, we see the DenseNet's latency does not rise. It still stays as 20 milliseconds per inference. But when the VGG16 comes up at 3 second mark, then we can see the DenseNet latency increased. So what we can see is like the uncontrolled spatial sharing is providing a better latency than temporal sharing, but for some applications, the latency is affected worse than other. Now, finally, when we see a controlled MPS sharing, we have allocated 25% GPU to DenseNet, 15% GPU to ResNet 50, and 60% to VGG16. Since each of these applications are getting percentage that adds up to 100, they are not overlapping over each other resources, and there is a resource isolation. Therefore, we see that the latency of each application does not change whenever another application comes up. We have much more predictable latency. There is no interference when something comes up or something goes down. And we can also see that one thing we should note that is DenseNet gets the latency of 20 milliseconds with just 25% of GPU. In other cases, we saw that giving 100% GPU to DenseNet also got us 20 milliseconds. But here, just giving 25% GPU also got us 20 milliseconds. So if we have a proper choice of GPU percent, we can achieve good latency for all this DNN. And we can see from this experiment itself that we got around 65% lower latency for DenseNet while compared to the temporal sharing. We should also discuss another method of spatially sharing a GPU. It is called Cuda Streams. The Cuda Streams are actually older than MPS. They also provide spatial sharing, but they look like a default MPS case. We experimented with the Cuda Streams, and if we can see the figure, we can see that inference throughput of ResNet 50 increases when we increase the number of streams. When we go from 1 stream to 2 stream, the inference throughput increases. But beyond that, going from 2 to 3 and 3 to 4, we can see only the latency increases, the throughput does not. Therefore, we start seeing a diminishing return on latency. As control MPS spatial sharing provides a way of allocating resources for each application a user can define, and in the stream, we cannot define it. It is also taken care by the GPU runtime itself. We prefer to use that MPS with control sharing over Cuda Streams. Now, we will explain another feature we have in our ML framework. And ML framework has to be able to facilitate low latency notification from GPU. The GPU executions are usually asynchronous with respect to CPU. Once you launch something on GPU, the CPU forgets about it, and the GPU will be processing that work. There is a Cuda API method called callback. The callback puts a tag on the end of an ML application kernel, like the yellow mark here. The ML application kernel finishes, then it executes the callback, which then triggers a callback execution function in the CPU side. While the callback it's very convenient that callback lets you know that ML application kernels have finished working, it has some limitations. First, the callback function blocks any further execution in the GPU until the callback function execution is resolved in the CPU side. And second, that callback execution in the CPU side cannot launch any other Cuda API function. Therefore, what happens is once you trigger a callback, there is a function, a new thread is started in CPU side, and it cannot do anything other than letting the CPU know that something in the ML, something in GPU has completed. It cannot launch another task at all. So a gap can happen while the callback execution is being processed by the CPU side. To remove that gap so that we can increase the GPU utilization, we use a method where CPU can query GPU periodically, say every 1 millisecond, to check if an event added at the end of ML application kernel is processed or not. There is a Cuda event API called Cuda event query, which is very lightweight API call that only takes 5 microseconds to resolve. And you can tag an event after every ML application kernel. So the CPU will check every millisecond if the event has happened. And if the event has happened, the CPU knows that previous ML application kernel has finished, and then it can launch another ML application kernel. In this case, the CPU thread never goes out of the context, as in callback case, and can launch another ML application kernel immediately. Therefore, there is very little or no idle time at all in GPU, and the GPU utilization is increased. Now I will discuss another module of our application that is called NetML module. It facilitates for low latency data transfer to GPU. Usually, what happens is the streaming data comes into the machine where the GPU is, and it has to be transferred from this host memory or the system RAM to the GPU RAM. It is usually done by a method called CPU copy. So incoming data from the packet payload is copied into a contiguous buffer in the CPU side before transferring into GPU for ML processing. What we use is we build upon our previous work called NetML. NetML cuts the extra copy, the copy you have to do from network packet to a contiguous buffer. It utilizes a GPU DMA engine to perform the scatter gather of data from the packets itself. We extended the original NetML to be able to create batches of application data in GPU. We added a lightweight mechanism to verify if the whole application unit data, such as image, is already in the CPU memory or not before initiating the DMA transfer to GPU. And we form a batch in the GPU in a contiguous GPU buffer so that we can have a batch execution of batch inference of ML data. So what NetML helps us with is NetML helps us reduce the CPU load. We measured the impact of data transfer from both NetML and CPU copy in terms of CPU load while transferring the data. We present the relative CPU cycles for transferring image data from packets with two alternatives. One is CPU copy, another NetML, and how much time it takes to infer and we inferred that image with the LXNet DNN model. We defined relative CPU cycles as cycle taken for transferring the data to GPU divided by the total CPU cycles for performing the whole inference. We can see that as the batch size increases from 1 to 4 to 8 to 16, and the data size increases for the transfer of the data, we can see the CPU is taking more and more cycles to copy the data into a contiguous buffer before transferring to GPU. In fact, when there is a batch size of 32, around 45% of CPU cycles are just spent copying data from packets to another CPU location before sending it to GPU. While in NetML, since we involve the GPU to do the transfer, involve the GPU to do the DMA, we can see it uses a very, very little cycles to transfer data to GPU, and this amount of cycles used to transfer does not grow as rapidly as in case of CPU copy. Now we can see how it affects the throughput of inference. We then used an LXNet model for inference, and we fixed the batch size to 8 for inferring and measuring inference throughput. We were able to deliver multiple images from network, and we were able to generate up to 6,000 inference requests per second. Now, as you can see from the plot, the NetML performs better beyond 2,000 images per second request because it has a very little CPU load while transferring image, while the CPU copy lags behind because a lot of CPU cycles is spent just copying the data to get it ready to transfer to GPU. We can also see that NetML throughput flattens around 4,000 images per second request. This is because of the limits on GPU rather than anything to do with the data transfer. The GPU can only process 4,500, nearly 4,500 images per second in this model. Now we will explain how our framework works with multiple DNN models, multiple DNN platform to make everything run together. There are many platforms available today, like CNTK, Darknet, MXNet, PyTorch. Some of them are just research platforms, but some of them are seriously deployed industrial platforms like PyTorch or TensorFlow. And they have a lot of variations. Some of them run with Cuda, some of them run with OpenCL, some of them support both. Some lack features of Cuda Streams. Some don't even support batching. And most importantly, they have a different startup time. Like CNTK starts up very, very fast. When you load a model, it only takes 2 seconds to start working, while TensorFlow takes around 10 seconds. This is because all of these applications, when they start up, either some of them grab the entire GPU memory and start allocating it themselves, but while something like CNTK does not do anything on GPU until the inference has started. Therefore, the loading of the model is very, very fast in those cases. So though these ML platforms are varied on many features, but we have isolated, or we have taken out like some of the important features that are necessary for ML inference. And we have summarized it as following 5 features, 5 functions. So there is always an initialization step of an ML platform when it comes up and it touches the GPU and it allocates the GPU buffer. Then the second step would be usually loading the DNN model. There are multiple DNN models it could load, so it has to select one and load it into GPU. The third one being transferring the data from CPU to GPU for the inference. Fourth being the inferring that data itself in the GPU, and the last being after inference obtaining the result and taking it back to the CPU side. So our framework, what we do is we write a callback API for these 5 operations so that we can easily integrate any ML platform we observe. So PyTorch, TensorFlow, or any other platform, we have the same setup callback API. We link with them and be able to run those ML frameworks and their models. And in the end, I would like to say the conclusion. With the relatively limited amount of computational capacity, there is a need to have better utilize CPU, GPU resources at the edge cloud. To do that, we propose an ML framework that adds a control spatial sharing in the edge cloud, edge cloud, which provides predictable inference latency, higher inference throughput, as well as shares the GPU much more effectively. The second, we have a mechanism to provide timely notification from GPU to improve the latency and utilization. And third, we use a small GPU kernel to help fully utilize the GPU resident DMA and can substantially relieve the CPU load and also improve the inference throughput. With the framework we have now, we can see up to 65% reduction in latency for some of the DNN model while multiplexing GPU. And we can also see that the throughput of some DNN model we can increase 1.6 times by using this GPU resident DMA. Thank you.
Okay, thank you very much. Is there any questions? Okay, if there is no question, let's move to the next speaker, and let's thank you again for the presentation from Aditya.
Thank you.
Thank you. Yeah, the next speaker is Professor Junshan Zhang, and it is also the first keynote of this workshop. Beforehand, I'd like to briefly introduce Professor Zhang. Professor Zhang is a fellow of IEEE, and he is currently with Arizona State University and has been the Fountain Chair Professor since 2015. His research interests include information networks and data science, including communication networks, Internet of Things, fog computing, social networks, and smart grid. Based on building on his research findings, he co-founded SmartPly Inc. in 2015, a fog computing startup company delivering boosted network connectivity and embedded artificial intelligence. Professor Zhang was a recipient of numerous awards from NSF, IEEE, and ASM. He was also the TPC co-chair for a few major conferences in communication networks, including the IEEE InfoComm 2012 and ASM MobiHop 2015. He was the general chair for the IEEE Communication Theory Workshop 2007, Web Opt 2016, and ACM IEEE SEC 2017. He is currently serving as the editor-in-chief of the IEEE Transactions on Wireless Communications and the senior editor of the IEEE ACM Transactions on Networking. The title of his keynote is Edge Intelligence in IoT Ecosystem, a continual edge learning approach. Let's welcome. Professor Zhang, I will quit sharing and please share. Yeah.
Thank you so much, Rongpeng.
Thank you.
Hi, everyone. It's great to be part of this program. Thank you so much, Rongpeng. You can.
Yeah, I can hear and see the screen. Yeah, no problem. Yeah.
Okay, I'm going to present some results on edge intelligence. So edge intelligence is an emerging new research area. It's basically a marriage of machine learning and edge computing. Over the past few years, we've been studying edge learning, edge intelligence from a continual edge learning perspective. All right. Okay. So I'll start with the big picture. Over the past decade, there's been a lot of talking about smart things, smart Internet of Things. So back in 2008, 2009, when there was an energy crisis, the governments across the world invested a lot on smart energy, smart grid. And in 2012, 2013, smart city, smart highway received a lot of interest. More recently, smart mobility like Uber, Lyft, right? And the smart buildings are gathering a lot of interest. Okay, so if I look at these smart things more closely, they all reside at the network edge. You look at the smart hospital, if you can see the mouse, smart hospital, smart building, they all live at the network edge. Each of these smart things is a network by itself, is an edge network, and it's connected to the cloud, right? The cloud, and we receive services from the cloud. So with a little bit of abstraction, we can view the Internet of Things, IoT ecosystem as continual from edge to cloud or from cloud to edge. Okay, so from edge to edge, they communicate through the cloud. They're connected through the cloud, and each of them receive services from the cloud. Okay, so how many edges are there? There are tons of them. Tons of them. Okay, many of us have heard about. We just talked about autonomous driving, right? And many of us are familiar. Familiar with the 5G or augmented reality, just to name a few, right? So in 5G, for instance, there are three pillar services. Number one, high bandwidth. And number two, ultra low latency services. Number three is edge computing. Okay, so you look at the out here, the 5Gs here. So 5G, some of the services actually, have very stringent latency requirements on the order of like a millisecond, and this is the case for autonomous driving, right? Okay, so based on the latency, we can categorize edges into, say, 4 categories. So, it's a very stringent service requirement in the range of like 1 to 20 milliseconds. And then next category is 20 to 80 milliseconds and so on and so forth. All right. So the message is that the era of edge intelligence is here, is coming. And over the past few years, big players, major big players in the industry, such as Qualcomm, Microsoft, Google, Intel, NVIDIA, they're working hard, they've been working hard to embrace edge intelligence. And there's an article published in Forbes actually saying the edge, AI at the edge, or edge AI is going to be the next gold mine. Okay, so actually there are already many smart IoT Internet of Things in the making. We're just talking about autonomous driving. And you may have heard about the robots made by Boston Dynamics. So these robots are very, very intelligent. They can do yoga. They can even, very recently, these robots actually can do shooting at some target in a very sophisticated environment. Okay. So a fundamental question is, how can we achieve edge intelligence to make smart IoT, to make IoT things, Internet of Things, smart and smarter, right? So that's the fundamental question here. If we step back, say if you buy a pet, how do you make it? How do you make the pet smart? You train it, right? Same, we need to train IoT devices, okay? So how do we train IoT devices? We need the data, right? Okay, so just to give you a more concrete sense of data, the big data, let me give you some numbers. So from the dawn of civilization of human being to year 2003, over a course of like 5,000 years, human being generated 5 exabytes of data. So how much is the exabyte data? How much is the exabyte? 1 exabyte is 10 to 18. Okay, it's huge, huge number. Okay, so over a course of 5,000 years, human being generated 5 exabytes of data. Okay, and a recent report by Cisco tells us, so by year 2025, so it's from over the course of like 2003 to 2025 is for 22 years, the cloud will have generated 20.6 zettabyte of data. So 1 zettabyte is 1,000 exabyte. So roughly it's about 4,000 times, right? So over a course of like 22 years compared to a course of like 5,000 years, the amount of data generated by cloud would have like 4,000 times. What is more amazing is this report also indicates that by year 2025, the edge will have generated 175 zettabytes of data. That's 8 times more, roughly. So that's because there are so many billions of IoT devices. Another report indicated that by year 2025 there will be 500 billion IoT devices. Okay. So there was an article actually called big data called tsunami of data, and they say this tsunami of data could consume 20% of the global electricity by year 2025. 20% of global electricity. This is just really amazing. Okay, so to make edge IoT devices smart, right? There are a number of challenges. Just to summarize, the data volume is just explosive. Right? It's more than double exponential growth. Okay, and this would be overwhelming if we had to use the traditional conventional approach using based on the cloud. Okay. And perhaps even more important, many of these IoT applications require real-time edge intelligence. In a sense, the decision making has to happen right here, right now, at the network edge. So the latency requirement is very, very stringent. Okay, so to tackle these challenges, Yeah, a consensus, a general consensus is we need to marry edge compute and AI in a sense of like pushing services used to be done at the cloud, at network core, and we push these services to the network edge in the physical proximity of these IoT devices. Okay, so to gain the edge intelligence, this is non-trivial. As we just talked about, the conventional cloud-based approach would not work well because it hangs upon the transporting the data from edge to cloud, and it can be slow, and also is a waste of network resources, and also they could be privacy concerns because much of the data, right, they have maybe personnel. All right, so just to recap, edge computing offers a number of benefits. We just talked about latency. It offers low latency, and it can be more energy efficient, and it offers higher bandwidth, and they give us better privacy protection, and so on and so forth. So it is our belief the marriage of edge compute and AI, that's the right approach, is the promising approach for us to attain edge intelligence. Okay, so if we view AI as the superstar, like Tom Brady in this picture, use New England and the Patriot team, right? So if we view the AI as superstar, edge computing as the rising star, elegant marriage between the two, the teamwork will give us edge intelligence. Okay, so over the past few years, we been working on edge intelligence. Broadly speaking, we use edge intelligence to refer to EI, the edge intelligence, EI model training, model inference, by making use of all available data and resources across the hierarchy, all the way from the bottom, right? From edge devices to edge nodes, edge servers to cloud data center, okay? So we classify edge intelligence into 6 levels. This is a pyramid. It's reminiscent of the 6 level of, the 6 level of for autonomous driving. In fact, we draw this. I draw this pyramid actually inspired by that. So we categorize the edge intelligence into 6 levels. At the very bottom is the current state of art, cloud intelligence. So in cloud intelligence, model training, model inference, they are all done, both are done in the cloud. Okay. So next 3 levels are like the first 3 levels of edge intelligence. So level 1, 2, 3, the model training is done in the cloud, but the model inference is done at the edge. So the different combinations at the level 1 is the cloud edge, they do co-inference. Okay, level 2 is in-edge inference, and then level 3 is on device. So from edge server to device, level 3, so on device inference. And then level 4 to level 6, the model training is carried out at the edge, so level 4 is cloud edge cloud co-training. Level 5 is all in edge. Level 6 is the ultimate limit. We want to push the limit, right? Ultimately, we want to push the model training on device. And this is very, very challenging. It's very forward-looking, very much like autonomous driving. It's going to take many years to come. So the benefit, one significant benefit is that, as we move up across the levels, the amount of data offloading from the edge to cloud would have become much, much less. Okay, so for model training, there are different architectures can be used. For instance, it can be centralized, it can be done at the network, can be done at the edge server, can be done decentralized in a decentralized manner. The training can be done on devices, for instance, or can be hybrid between the two. Okay, some key performance metrics include latency, how fast your model training is, and what is the accuracy, the loss, right? In terms of loss function, what is the accuracy, and what's the how is the convergence behavior, and the other metrics such as privacy protection and communication cost. These are the key performance metrics for model for edge intelligence. So here's the big picture, and having talked about it, and our focus is over the past few years been we try to make attempts to study model training, edge model training, using so-called continual edge learning. Elaborate what it is. All right. So, okay. Model training at the network edge. Okay. So what it is, right? So let's first look at a standard machine learning problem. It is so we want to choose a model that can minimize the overall cost, right? This H is the cost loss function, and then depends on your model parameter, of course, and also depends on data. We have a lot of data set, okay, denoted by KC. So KC is your data, and it follows some probability distribution, but it's unknown, right? Okay, so oftentimes we use empirical risk minimization to replace this stochastic optimization. All right, okay, so this is underlying distribution P is unknown, and we have data, and we try to minimize. We try to train and to find a model W to minimize the corresponding loss. So this is a standard machine learning problem. Now, when we have this problem at the network edge, there are a few new challenges. Excuse me. Yeah, number one, although the amount of data at the network edge is humongous, but each individual edge device, the available number of samples is limited. Okay. Number two, at the individual edge device, the corresponding computational power is also limited compared to the cloud data center, and this is very, very limited. So if we had to train a model at each individual edge device, it's going to be very, very challenging. So what's the right approach to do it? So that's the question we've been thinking hard over the past few years. So we believe continual edge learning is a very promising approach to tackle these challenges. So what is continual edge learning? So continual edge learning is basically continual learning used at network edge. Let me elaborate. Okay, so continual learning, this is sometimes also called a continual lifetime learning. It's a machine learning paradigm. It's designed to sequentially learn from data samples corresponding to different tasks. So tasks arrive in a sequential manner. You learn one task and then continue learn across tasks in a sequential manner. This is called intuitively, makes sense, right? It's continual learning. Okay, so the idea here is rather than learning the new model from scratch, continual learning can design algorithms by leveraging knowledge transfer from the past, from previous tasks, right? Pre-trained models, try to leverage that knowledge transfer from pre-trained models to speed up the training for the current edge learning task. Okay, that's the basic idea for continual learning, and when we apply it to edge learning, we also need to take into consideration the challenges for edge learning. Limited amount of data at each individual edge device, also limited computational power at the individual edge devices. So, one key assumption in continual learning, which is the case in edge learning too, there's no access to data set from previous tasks. Sorry, there's a typo here. So no access to data set from the previous tasks. Okay, so there's some major challenges in continuing edge learning besides the few challenges we just talked about: limited local data and the limited computational power at the edge. There's another also challenge common to continual learning, so which is called catastrophic forgetting. So catastrophic forgetting refers to the following. Okay, so intuitively, whether we can use the model learned from the previous tasks, right? We can use it as a starting point and then fine-tune it to fine-tune this model for the new task. But by doing so, actually, intuitively, it would force the new model parameters to fit new data, which eventually, right, would yield poor performance, poor representation of the predictions learned from the previous observed tasks. Okay. So this is so-called catastrophic forgetting. This is common for continual learning and continuing edge learning. So that's something we have to, have to pay close attention to when we devise continuing edge learning algorithms. So a couple of main, sort of like main techniques used to combat catastrophic forgetting. Number one, regularization. Number two, experience replay. Number three, parameter isolation. Number four is dynamic neural network architecture. So all these studies, these mechanisms have been, are sort of like in the past, in the existing literature, are used in the context of neural network training. All right. So one main objective of our study is to come up with a systematic approach to try to get a more fundamental understanding of continual edge learning. So, so I'm going to, in the next, let's say about 20, 25 minutes or so, I'm going to present you three problem formulations we have developed. Okay, so the very first one is continuous supervised learning using so-called all-in-edge learning. Okay, so all-in-edge learning meaning the model training is done 100% at the network edge, completely at the network edge. So this is clearly very challenging. So to do that, we take a so-called distributional robust optimization approach and try to make use of these mechanisms, regularization, experience replay, okay, to combat catastrophic forgetting. Okay, so let's look at this problem more closely. So we have pre-trained model either in the cloud, training in the cloud in the past, or from other edge tasks. Okay, so we have a pre-trained model, and we want to transfer knowledge from pre-trained model to, say, a new edge learning task. Okay, but at each individual edge node, there's a limited number of samples and also limited computational power. So the question is, what is the right abstraction, right, of knowledge transfer from previous tasks? We need to come up with a good abstraction of the knowledge transfer from previous tasks so that we can integrate it cohesively with the local edge learning. And this is highly non-trivial, right? So you come up with this abstraction, but how can we combine, how can we integrate it with local edge learning based on empirical risk minimization? How can I do that? Okay. So this DRO approach, distributional robust optimization approach, actually offers a nice marriage of experience replay and regularization. Okay. How do we do it? Okay, let me elaborate. Okay, so from previous tasks, we learned some models, say we denote as W sub C, right? And the corresponding data, X and Y, is just like we are talking about supervised learning. So X is the data, Y is the label, right? Okay, now the data distribution from the previous task, say denoted as PC, That's something we can learn from the past. Once we learn the model, when we have an idea about the data distribution model, right? But this data model, data distribution model is relevant to the data at the network edge, but it's not directly applicable. So there's ambiguity about the PC, the data distribution model from previous task. Okay, that's one observation. So there's ambiguity about it, about PC, when applied to the training at the network at the edge. Now, if we observe the data at an edge device, because it has a limited amount of data, then the corresponding empirical distribution, empirical model is also is away, distant from the underlying model and the real model, underlying model. There's also ambiguity or uncertainty. So if we look at both, right, the data model from previous tasks and also the local model at the edge, both have uncertainty, both have ambiguity. So to build a cohesive integration, for each of them, we construct a distributional uncertainty set. One centered around PC. This is the data model from the past, from previous tasks, and the one is based on local data, which is also, because of limited amount of data, is also distant from the underlying model. Okay, we can construct two distributional uncertainty set, one based on local data, another based on the PC, and then we can combine them. We can treat both as constraints. Okay, in this way, we can send them as constraints, or we can come up with the DRO formulation, distributional robust optimization formulation for continual edge learning. So let me just recap. So for local data, we have an empirical model, P0. We construct a distributional uncertainty set, okay, centered around it, P0. And then we have a reference model, PC from the previous task, because it also has uncertainty, it offers uncertainty. We can construct another distributional uncertainty set. This is for the knowledge transfer. So we now have two distributional uncertainty sets, okay, and then we can treat them as both. We can put both as constraints, okay. The given right here, the constraints, and then the problem for continual edge learning reduces to choose the right model subject to the constraints. Okay, so in this way, there's two constraints offered by the distribution based on the distribution uncertainty set, right? It gives us a nice, elegant marriage of experience replay and the regularization. So they are treated as regularizers, and also by using the distributional uncertainty set as a constraint, right? And then we use, it gives us experience replay of the data, synthetic data from previous task. Okay. So just to recap. So this DRO approach for continual edge learning gave us a nice marriage of experience replay and regularization to combat catastrophic forgetting. So by using a duality approach, then there's a detail I skipped here. This problem can be reduced to two-tier optimization. Depends on the loss functions, convex, non-convex, different ways to solve it. Okay, if we look at this equivalent formulation of the optimization problem, you can see the rows of local data corresponding to P0 and the synthetic data generated by PC, which the reference distribution transferred from the previous task, right? So the synthetic data generated by PC is basically the experience replay, and the P0, the data corresponding to P0, that's the local data training. So nice marriage. They're sort of like playing the same role. Okay. All right. So I can show you quickly some experimental results. We apply this method to logistic regression, and it gave us these experiments tells us give us some like a nice gain. When we use this edge cloud synergy compared to edge training only. So in the interest of time, let me just zip through this, and then we move on to the next, the second formulation. Okay. So in the second formulation, we look at the continual supervised learning by using federated meta learning. Okay. So federated meta learning is built upon federated learning. Is actually a marriage of federated learning and meta learning, and the model training is carried out by using edge cloud co-training. So you make use of the computational resources that both edge nodes and also the cloud. Okay. So as illustrated in this view graph, in this diagram here. Okay. So suppose we have pre-trained a model in the cloud, and the model parameter is generated by theta c. So we transfer this knowledge from the cloud to edge for edge training. And then at edge, we have multiple devices. So we call it source edge nodes. Many of them, they collaboratively train the model further, right? With the help from a platform. This is the structure of the architecture of federated learning, right? And we use meta learning across edge devices. And so the federated learning takes into account of the knowledge transfer from the cloud, theta c, and then come up with a good model, meta model, denoted by theta at the here, if you can see my mouse. And this is used as a model initialization. And based upon that, okay, at the target edge node, it is local data, dynamic data, and build on this model initialization, this edge node uses fast adaptation to come up to train a new model for the current edge task. So that's the basic architecture for federated meta learning in this context. Okay. So okay, so question here is how can we make a use of the knowledge transfer from the cloud intelligently to combat catastrophic forgetting? In the meanwhile, we can speed up the training for the current edge learning task. So that's the main objective for this study. Okay, so mathematical formulation is it's federated learning, so we try to minimize the overall and many multiple edge devices, say I of them. Each of them has local data, and let's use LI to denote the corresponding empirical loss based on local data DI. And so federated meta learning, the objective is to minimize the overall, the weighted overall loss function, and to incorporate the knowledge transfer from the cloud, we use the regularization, which is based upon so-called Bergman divergence. This is a very general divergence metric. It actually it's very general, encompasses many of the popular ones like KL divergence and Euclidean distance, so on and so forth. Okay, so we use this Bergman divergence because it is very general, and it serves as a regularizer to confine the learned model, the model to be learned to stay closer to the cloud reference model. So in this way, it can help to combat catastrophic forgetting. Okay. So that's the objective for this study, for this formulation. Now, how do you solve it? If you look at this problem, okay, how do you solve it efficiently to speed up edge learning? We use so-called inexact ADMM technique. Why do you want to do that? How do we do it, right? So because there are many, there are multiple, there are many edge devices, and they collaboratively to learn the model. So that's why we use ADMM, because it's a very promising technique for large-scale distributed learning. Okay, so by using ADMM, then we can at each edge node we can do local update. We can update the global model parameter theta, each of theta t, and then we have a local version of that. We update it based on local, but each iteration based on the global one. And then at the platform, we're talking about the edge cloud co-training. So at the platform, it does aggregations by solving this a lot of optimization problem. Okay, so the one difficulty, technical difficulty here is difficult to solve directly of the local subproblem. So that's why we use inexact ADMM. So what is inexact ADMM? So basically, you do local approximation to simplify the local problem. So you get an inexact solution, which is fine, right? And the benefit is it can speed up the convergence a lot. Okay. Another difficulty is the standard ADMM method requires hashing, the knowledge of hashing, which is a second order calculation. So to simplify it, we come up with what's a hashing free version of that. So this is why it's called ADMM based hashing free approach. Okay. Okay, so here's some experimental results. Because of time constraint, I skipped the gory details. If you're interested, we can talk offline. Okay, let me just present you some experimental results. So we have carried out extensive experimental studies, and this is so you look at data set we have here is we use the MNIST, we use CIFAR 10, CIFAR 100, and our approach based upon the inexact ADMM local update. It does only one. It requires only one local update compared to other methods. See where the top is ADMM at the very left, at the very right. The accuracy for MNIST is about 95%. It's pretty high. We're using only one local, each iteration we're using only one local update compared to other sort of like state-of-the-art algorithms, Federated average and the personalized Federated average. They use even more local updates, but the performance of our algorithm is quite a few percentage better than the current state-of-the-art algorithms. And we also run experiment using CIFAR 10, CIFAR 100, which is more sophisticated database. You can tell the gain is still very significant. Even when other algorithms using federated average and personalized federated average, using 10 updates per iteration, they get one federated average gets about 56, 57%, and the personalized federated average algorithm gets about 67%. Now our algorithm give us 74 plus percentage accuracy. Okay. And the performance actually for more sophisticated database like CIFAR 100 is even more pronounced. So, and to examine the impact of the knowledge transfer from the cloud, we look at different combination by checking, by varying different numbers. Number equal to 0 means we don't cooperate the knowledge from the cloud. Number equal to 10, we give reasonable weight to the knowledge transfer from the cloud, like theta C. And number equal to 50 is much higher. So you see, the knowledge transfer from the cloud does help. And if you give too much weight to that, and then the training accuracy degrades. All right. Okay. So let me see. 740. In the next 5-10 minutes or so, I'll quickly zip through this the third formulation. So in this formulation, we look at a continual learning of generative models. So why do you want to study that? So if you recall, in the very first formulation, we want to use the experimental replay to combat catastrophic forgetting in continual edge learning. So how do we do it, right? We need a model to generate synthetic data. We don't, because for the current task, there's no access to the data set from the previous tasks. So the right approach is to get synthetic data. How do we get synthetic data set samples? We need to have a generative model. So this is why generative model, plays a very important role in continual edge learning, or in continual learning in general. So, so now in this problem, we want to study continual edge learning of generative model. So how do we do it, right? Okay. Okay, so we are going to use generative adversarial network GANs, right? Many of you might have heard about it, and especially we're going to focus on Wasserstein GAN. Okay, so you look at the view graph at the very bottom. So for those of you who are not so familiar with GANs, right? So look at the bottom of the view graph. For GANs, there's a generator and there's a discriminator. Okay, so the generator, they work in concert to come up with to develop a generative model. So eventually, after training is done, the generator can generate samples very similar to the original data set if it's done well. Okay, that's the basic idea of GANs, generative adversarial model. Okay, now, so the question we face here is how can we leverage pre-trained? So suppose there are multiple edge nodes. We are trying to train a new model, generative model, for a new edge learning task. So how can we leverage pre-trained generative models from other edge nodes to facilitate the continual learning of a new model based on local edge data set only? Okay. So mathematically, we can treat it as a constraint optimization problem. So here we talk about Wasserstein GAN. So we choose, the idea here is we want to choose a generative model, new, which minimize the W Wasserstein distance between your local data set represented by the empirical model, mu zero hat, and new, that's the one you are trying to get, right? Generative model. Try to minimize the Wasserstein distance. Now, with constraints are built upon the knowledge of the pre-trained generative model from other edge nodes. So suppose there are k of them. For each of them, you already have a pre-trained model. So then build upon that, and then we build a distributional uncertainty set and treat it as a constraint, very much in the same spirit as the DRO formulation. So just to recap, we have a constraint optimization problem. Our objective is to choose a generative model that minimizes the Wasserstein distance between the goal, the generative model new, and also your empirical data. Subject constraints, each of the constraints is built upon the generative model pre-trained in other edge nodes. Okay, and it turns out we can use Lagrange relaxation by choosing the right Lagrange multiplier is 1 over eta. Eta k is the ball size, the spin of ball size for k pre-trained generative model, and then we can treat it. We can cast it as by using Lagrange relaxation, we get the following formulation, which turns out to be a so-called Wasserstein 1 Berry center problem. Okay, so now based on this formulation, then the next step is to find the solution, right? So-called Wasserstein 1 Berry center. So how do we do it, right? This is technically non-trivial. It's challenging because it's different from like you can eat in space. You give you a few points. You can try to find at the center, right? That's sort of like intuitively. That's the analogy. But now we're looking at a functional space. Each point in a functional space is a probability distribution. So it's not a Euclidean operation. So it's it's much more sophisticated. Between 2 points, say pre-trained generated model G1 and another one G2. The minimum distance is so-called geodesic curve, right? Is more sophisticated. And then there are k of them, and we have a local data. Then we try to find the Berry center for these distributions. So that's the main problem we are trying to tackle here. Let me just skip the details here. Let's look at the architecture. How do we do it? So, so the basic idea is the following. There are k of the pre-trained generative models with the offline training. Now, good thing about a generative model is that it takes much fewer parameters to describe data set. It can be transferred to the cloud. Now, even with that, the training can take time. So we come up with a recursive algorithm. Each instant, for each recursion, we try to come up with a coalescence amount between 2 models. Say node 1, node 2, we come up with mu1 star, and then so on and so forth. We do it in a recursive manner and try to find the coalescence of k pre-trained generative models. And then we use that model as the sort of like a model initialization for faster adaptation at the edge, combined with the local data. And then besides the 2, UK star and the empirical local data, and then we find the generative model at the node, say, the new edge node 0. So here's some details for the GAN architecture, what's the GAN architecture, okay? So this is we're looking at a kth iteration, kth recursion, and then based on the last step iteration, we use that to generate synthetic data combined with the new one, and then we find a Berry center solution. So this is can be done in offline, either in the cloud or at the networks at the edge server. So and then this is the sort of like a high level picture of this recursive algorithm. Okay, every step, we do it in a recursive manner. Each recursion, we try to find the Berry center among 2 models, pre-trained models, and so on and so forth until we come up with the coalescence for all k pre-trained generative models. And once we do that, and then we use it as the input combined with the local data and train a new Watson GAN. Okay. All right. So we have done some theoretical studies and also experimental studies. In fact, we have done a lot of experimental studies. And this is just one experiment result to illustrate the improved gain by using our recursive algorithm compared with if you just do training based on local data only, right, without the knowledge transfer from pre-trained generative models. So clearly, this blue one is this FID score, the lower the better. The blue one is the very, very top edge only, and you see the recursive algorithm give us results at the very bottom, which has the lowest FID scores. Thank you. Yeah, I've used about 15 minutes. I think I'm going to have a few more slides. Let me just conclude. These are some applications. So just to summarize, okay, we view the IoT ecosystem as the edge to cloud continuum. Okay, to make the IoT devices smart, we have to train them, and we advocate continue edge learning to train edge models built upon the knowledge transfer from the previous tasks. Okay, and the one important object here is to combat catastrophic forgetting. You learn from the past, and if when catastrophic forgetting occurs, and then as time goes on, your model would be representation of the previous tasks, previous data. So this is not very good. That's why we want to combat it. And for continual edge learning, I present you 3 formulations using different techniques to combat catastrophic forgetting. Experiments we play, regularization, are very promising techniques we can use in continual edge learning. So I'll stop here. I look forward to the questions.
Okay, thank you very much, Professor Zhang. Is there any questions?
So I zip through it very quickly because of time constraint, but there are many details.
Yeah, actually, I personally, I think the continual edge learning is a very interesting idea. I have some question I'd like to first raise, and then we can hear some further questions. My question is that what is the relationship between continual edge learning with other concepts like, for example, transfer learning or other learning, or few shot learning? Or what's the relationship or difference with between them?
So this is a very good question. The question is about what's the relationship of continual edge learning with, say, transfer learning, feature learning. Okay. Yeah. So continual edge learning is sort of like a big umbrella that, for example, we have talked about in the second formulation. We talk about meta learning. So meta learning is one sort of like a very promising technique for feature learning. Right. In the second formulation, let's go there. Yeah. So I didn't get time to elaborate because, okay, this is it by itself can be a 1-hour talk. So federated meta learning is a marriage of federated learning and meta learning. Meta learning, basically you try to learn over many tasks to build a model initialization, and based upon that, use fast adaptation to achieve feature learning. That's the idea behind meta learning. So what I'm saying is that continual edge learning is a big umbrella, and we can use many techniques such as transfer learning and feature learning under this big umbrella.
Okay, thank you. Is there any questions? Okay, actually I have a lot of questions. My second question is that it seems that you mainly talk about the single agent learning, even in spite you talk about the continual edge learning. But at the edge, many devices are connected with the edge. I mean, it is highly possible for multi-agent learning or something like that. How do you envision that the progress of the continual edge learning from a multi-agent perspective?
Okay, so the question is about so for continual edge learning, how do we do single agent learning versus multi-agent learning? The first formulation is we look at the first formulation. We look at the continual supervised learning, sort of like from a single agent perspective, right? The knowledge transfer from the cloud to a local edge node, and how do we build a synergy? How do we build a synergy to integrate knowledge transfer from the cloud and the local data, local edge learning? How do we make them work in concert? And in the second formulation, actually, is about sort of like a network agents, many edge nodes. They're working together. They collaboratively train the model together with the help from the platform. So this is multi-agent learning. It's federated learning, right? So there are many edge nodes. Each edge node has some data, but not enough, right? But many of these edge nodes, they work together, try to train the edge model. Excuse me.
Okay, okay, thank you. Is there any questions? Okay, if there is no further question, I'd like to thank you, Professor Zhang, once again, and like to close this session. We will have a short break, and then we will have the session D of today's workshop. Thank you, Professor Zhang, and thank you, everyone.
Thank you.
Thank you.
Okay, I'll stop recording now. Feel free to use this call as a chat during the break, and I will start recording in the next session.
Okay, thank you, Noya.
Thank you.